Yeah, so it's glad to see so many of you joining. It's so glad to, in case anyone has to leave early later, let me just say this. I'm really proud of everyone sticking in this course all the way to the end. As I said many times from the first day, this is probably the most difficult physics course, or even one of the most difficult courses you would do in college, especially packed into 5 weeks. Congratulations for sticking to the end. Well done. And like I said, from the beginning of the class, my goal, really, I mean, there's the goal of learning the physics, but ultimately, my main goal, I have two main goals. Number one is learn how to learn difficult topics on your own, because that to me is that is the point of college. If you ask any professor, that is the ultimate goal, even though it's not communicated as often. So learn how to learn things on your own. You don't expect to be spoon-fed. Hopefully I've done the job, and as a instructor, as a professor or instructor or to a course, our jobs is to hopefully to motivate you and give you ideas. Number one is to narrow down the vast topic in the textbook. As you see, there's a lot of advanced topics that is starred in the textbook, and also due to this course, I also limited the scope in the syllabus. Part of our job is to tell you which ones are the most important things to take out of the course, at least what we want you to take out of the course. And also the second job of us is to motivate you and give you sort of the bigger context, things that are not discussed in traditional books, in some sense that way, and not to just word by word, just copy out the whole textbook in front of here. Otherwise that is a waste of lecture time. It's completely redundant. So hopefully I've done that job. And then second goal of myself is to, it's a more selfish goal, more personal goal, to hope to be able to share some of the interesting things, some of the amazing things, some of the wonders and joy in physics, some of the big ideas, some of the deep ideas, some of the practical ideas. Hopefully, so personally, this is my selfish side of the goal, is hopefully after this course, you also have a different view of physics. You go on forward, even though I know 99% of you are not going to become a physicist. That's completely fine. I'm not going to be a biologist, but I can appreciate, and hopefully this is one thing you can do, is to appreciate some of the ideas, some of the skills, as well as ideas from physics, and have a good impression from this. All right, without further ado, thank you very much, and we'll jump into talk about the syllabus. So let's see what's the best way to show this. Yeah, let's have this on this side. Cool. All right. So today I'll try to do 3 things. In the next 20 minutes, I'll try to go with, hopefully slightly optimistically, with 1 minute per chapter-ish, go tell you what probably narrow down to maybe like 3 key ideas, maximum 3 key ideas per chapter, to go through that. And then I just have to give you a few extra materials, because it's my class. And at the end, I hope I was able to save at least 45 minutes minimum to do all the problems you guys have so kindly voted in. Okay. All right, so let's start. So the first one is about, yeah, maybe I'll just put this on the side so I can focus here. Okay, so we started off the course with chapter 1 on mainly buoyancy. And the key formula over here is B equals to rho Vg. Okay. And again, it doesn't matter what symbol you use, it's what they mean. So this is the buoyant force. This is the density of the surrounding fluid. Okay, so that is one key thing you need to know, density of surrounding fluid. And this is basically a new contact force that we learn, that if you have yourself surrounded by a fluid, this fluid will provide a buoyant force. It's a contact force because it's in contact with the surrounding fluid. So it's good to put a F over here to remind yourself. And V is the volume submerged. So if you're only half submerged, this kind of makes sense because it's a contact force, right? If you remember the definition, the word definition of buoyancy is the upwards force due to an upward contact force due to surrounding fluids. So if you only half submerged, so sometimes you'll be asked to calculate a fraction, how much fraction is submerged. So that's the volume submerged over the total volume of the object. Only the part that is submerged will contribute to that buoyant force. So there's no one easy mistake is to plug in the volume, plug in the wrong volume. But if you understand really what this means, it's a contact force from the surrounding fluid, then there should be no confusion, because this part is not in contact with the fluid. So there's no reason you would put in the total volume here, only the part that is submerged. Okay, so I won't write out that part, but just to illustrate the key idea. So what we will be tested on, most likely, if it's an open response question, this is an easy, a very common open response question. It's easy to test. is to analyze free body diagrams. So technically speaking, it's all 3A with just a new type of force. So you should be able to ask yourself, just to recall, we'll do a little bit more about free body diagrams to illustrate exactly how to solve these problems. But as you remember, ask yourself the two questions, what's touching it and what's not touching it, non-contact, right? And sorry. Something popping up on my screen, just getting rid of this. All right, sorry. Yeah, so, and non-contact force. Once you do that, you write out Newton's second law. So or first law. So first law says that if the thing is not moving, then all the forces are balanced. So all the forces are balanced, or Newton's second law, which says if it is accelerating, then the acceleration is proportional to the net force. Okay, so in reality, you will add in gravity and stuff like that. So that's the key idea there. We brought on the term density, so that's a new terminology. In fact, for all the definitions, let me use blue. Okay. So definitions have a special place in physics. Definitions are always true, unlike formulas. Okay, so that is it's definitely worth memorizing. So technically anything in a box I would probably memorize, even though you have a cheat sheet or even though you have a formula sheet. Again, this is also, yeah, let me leak in some studying advice as well for you. When I say this, it's not to make your life more difficult. You have to understand that. It's actually to make your life easier, because if you know the formulas by heart, then you will actually make problem solving much easier, because you have this arsenal of things in your head to be able to use instead of trying to look it up every time. Okay, hope that makes sense. It should make sense intuitively, especially a lot of your biology students, and remembering definition shouldn't be a problem. So might as well play to your strength. Unless you're very good at problem solving, then you can look up, you know exactly what to look up. You know, a lot of my physics colleagues do that. I intend to remember more formulas than others, because I'm not as good as navigating through the confusing avenue of open response questions. So if I have things sort of at the arsenal in the back of my head, then it's much easier to pull things to use it without having to flip through things. Some of my colleagues, physicists, have a much better physics intuition. So they look at a problem, they already sort of have the intuition of what I should do. And then they will be able to look up the formulas to do that. But for me, and I think it will be useful for you guys as well, even though everyone thinks differently, I think, why don't work with your strength? If you're good at just remembering definitions, then you should do that. It should actually make your life easier. One of my professors in the past actually said, made a joke that your birthday and your social security number is something you look up, but definitions are something you know. So that shows you how important they should be. And in the way I look at it is, definitions is like reading a novel without knowing the words. If you don't know the definitions by heart, can you in principle read Harry Potter by looking up every other word every difficult word, every jargon? So technically you can, but that is, you defeat the point, and you won't be able to enjoy the story or even get a lot out of it, even understand the story that way. So definitions, very high priority. Formulas is my second priority. I would still do it, but this is how I would treat them, all right? Okay, so that's all with chapter 1, and then chapter 2 and 3, I'll group it together with static and dynamic fluids. From static, really, it's just a hydrostatic equation. Again, like I said, I always don't remember which one's which. So now I use a little bit of physics intuition to think, should the pressure, one is top, one is bottom. Which one is higher, which one is lower? The bottom pressure should be larger because you have more fluid on top. So this has to be bottom, this has to be top. Okay. And just to make sure you know every variable, use them correctly. The height, especially this one, is the height of fluid. So you're comparing 2 points. You're comparing this point. It doesn't have to be all the way to the top. It can be here. So these are potentially, it can be a long answer question. It can be a short answer question, because it's usually just a direct plug and chuck. You don't have to draw free body diagrams. There's no analysis, deep analysis going on, really. It's just, so it could work as both. Yeah, so it could be just comparing the top and the bottom like this. And in that case, make sure you use the right height. Basically it's the height of the fluid in between the top and the height of the fluid in between the top and the bottom. Okay. I probably wrote it out there's a more rigorous way in my notes in the past, but if you're asked for a definition, you don't have to recite word for word, although if you do, that will definitely give you the point. But don't worry, it's not really an English test. So if you can convey the accurately, then that's fine. It doesn't have to be word for word from the written definitions from that I provide. But of course, if you do, that will definitely give you the points. All right. Interestingly, sorry, one easy mistake is when you look at the pressure on the bottom. If you talk about absolute pressure, so sometimes we want to emphasize that we're looking at absolute pressure as opposed to gauge pressure. So this is a new definition. Gauge pressure is not really that important in physics. It's more like an engineering concept or an everyday life concept, because in physics, we just want to know the pressure, the actual pressure of things. But like I motivated, when you go into, if you go into medicine, become a doctor, and you measure the pressure of people's blood pressure, you probably don't want to add the atmospheric pressure. So you define a new concept called gauge pressure. It's the actual pressure or absolute. You can call it absolute or actual, whatever. Subtract away the atmospheric pressure because that is always there. All right, so technically the absolute pressure here, just in terms of a problem solving perspective, you technically have two fluids on top. You have air and you have water, right? So the real pressure over here is actually the pressure, it is the pressure on top, but so technically it's all the atmospheric pressure here that you add up plus all the pressure due to the fluid. And so this term represents due to the fluid. Okay? And you also know that this is basically a special case once you know Bernoulli's equation is this, right? So it's like half mv squared. It's like mgh, but just change all the m to a rho, and you will have the Bernoulli's equation. Okay, and one important thing to get out of this is to learn how to use the type of equations that says something equals constant. So you're used to equations saying something equals to something, but not as used to something equals to constant. But hopefully by now you're very familiar with both types, right? So by now you know how to use this is you pick 2 points to compare. So a more practical version, which I won't put it in the box because it's just basically the first one, is take 2 points and compare them like this. Right, so notice I immediately put in subscripts 1 and 2. So technically you might want to put in subscripts for the row as well if the row is not the same. So if you have a complicated problem like oil and water at the same time, so let's say here, if you have oil and water at the same time and you decide to compare these 2 points, make sure this point if this is point number 1, this is point number 2, the row over here you're using oil, the row you're using water. Okay. But most of the time, probably I would say at least 80% of the time, you will only have a problem with usually the same fluid in both points of comparison. Okay. And also there's the continuity equation when things are flowing. So that is AV equals to constant. And you should know how to solve these problems with something equals to constant. And a lot of times these two work in conjunction because you're given the area, but you're not given the velocity. So you can use this to find the velocity first and then plug it into Bernoulli. So maybe I'll put them as a link together. A lot of times, sometimes you just need one, sometimes you need both. Okay. I would say sometimes if the problem actually requires you to use both together, it will most likely be an open response question. Or if it's just a simple use one of these and just a plug and chug, it might be a short calculation, short answer type question. Okay. So that's all with part 1 about fluids. So the question here, if there's an equation that you write down that we are allowed, if there is an equation that you write down, are we allowed to add it to an equation? Yeah, sure. Yes, of course. Okay. All right. And then this moves on to part 2 about thermophysics. Okay. It consists of a couple of chapters. The first one mainly is about definitions. Okay. So learn these words. I'm not going to write out all the definitions. What is internal energy? What is temperature? Maybe I'll briefly just say in words. Internal energy is, I forgot actually. It's basically all the energy that does not contribute to external motions or not from an external source. It's a more elegant way to put it, but that is the concept, right? So remember, what is external energy? External energy is either just the external kinetic energy or or any gravitational potential energy or electric potential energy that is there's an extra source outside of the system that is providing energy to the system. Okay, so if this is your system, so this is also a word. We won't test you the definition of this, but you need to know this concept. It's basically an upgrade from the idea of objects. From 3A and also the first chapter, we'll not talk a lot about objects, but now we have gases, which is a lot of objects, right? So it's better to talk about the whole system like this. So we start to use the word system if we're talking about macroscopically like that. So if this thing is moving externally, that's an external energy. If there's an external source like the Earth providing gravitational potential energy or electric source or whatever, those are external. right? So temperature is a measurement of what is the average kinetic energy inside a system. And then there is heat, which is the transfer of internal energy due to temperature difference. Okay, because heat is always a transfer, so you use delta Q. I'll skip around these chapters a little bit. From the first law, you know that the internal energy, change in internal energy is how much heat you add and how much work done, right? So heat is basically the transfer of internal energy, as you can see from the first law, the transfer of internal energy that is due to purely from temperature difference, right? It's not due to you squeezing the box. So if you change the volume of this, then you will contribute to the internal energy as well. As you can see, this is also internal because it's not due to the whole box moving. It's not like the whole box moving around. It's you're making the volume smaller like this, right? So it's not one of the two cases that I said earlier. Either there's some external source or external motion. Okay, so this is the first law, important. So you want to remember that. Notice remember how to use the plus and minus signs of these. So I sort of translated this to volume here is because the work done, the definition is from initial to final, FDX. Okay, maybe I should say FDR because it can be in 3 dimensions. But if you're in 1 dimension, then you can just simply do this. And if the F is constant, you can pull that out and you only have delta X, which is from, right? If you actually do the math, right, do the integration, you'll have X final minus X initial after you pull this out and integrate. So this is the one you may learn in 3A, but hopefully you've also learned this version. In terms of gas, we can rewrite the pressure into force per unit area. So you can, I'm not gonna go through the detailed steps, it's just 2 steps in between, but you can rewrite it like this. So if the pressure is constant, if the F is constant, you can do that. If the pressure is constant, you can pull that out and get this. So as in most of thermophysics, when we talk about work done, it's basically any change in volume. It's related to that. More sophisticatedly, in a PV diagram, if you have a process from A to B in any way any one of those processes, the area under the curve is representing the amount of work done. Okay, so you can see that from here. So this is the definition. I'll put this in the box as well. It's important enough to know, even if not for this course, for free C as well. And this is useful for this particular part. So technically speaking, I would call this a formula, and this is a definition. Right? But sometimes this is so close to the definition that sometimes we would just even say this is a definition. But yeah, all right. So how do you know how to use positive or negative? If the volume is expanding, then you need to ask yourself, look at the question, is it work done by the gas or on the gas? Okay. So if the gas is expanding, it's very difficult to think about negative work. In fact, that shouldn't be it's not really a thing. It's you can't really have negative work, but in terms of intuition, but in terms of the mathematics, because the work done on something plus the work done by something should equal to 0, right? So whenever it's easy to think about which one's positive first, and then look at the other one. I'll give you an example. If this is an expansion, that means the gas itself is doing work, right? The gas has to do work to expand. So think about, you are a particle, you are a gas particle, you are boxed inside a box, and you try to expand the volume, so you must be doing work. Okay, so the work done by the gas is positive in an expansion. The work done on the gas as a result must be negative, just the opposite of that. Otherwise, it's very difficult to think of what is negative work done. Technically, you can, it's sucking in the work, but you know, it's not as intuitive. How about compression? So if I'm going the other way, if I'm compressing, so this time, which one is the positive one? Must be work done on the gas is the positive one, right? In order to compress it. So I would first think about which one is positive and then infer which one is negative. And then I will look back at the question and see, what are they asking? Are they asking on or by? And then I select the right sign. Okay, the magnitude, I'll just plug it into these formulas and calculate them without caring too much about the sign, and then plug that in at the end. Okay. Now circling back to delta Q. Delta Q depends whether it's a solid, liquid, or gas. Okay. So if it's a solid or liquid, usually the pressure is kept constant in any process. So as a result, any delta Q can be directly used in this formula. Okay. So this formula technically, sometimes you can label CP. This is the specific heat capacity kept measured at constant pressure. Okay. So this formula is appropriate when the pressure is constant. And for liquid, when you're compressing it or trying to heat it up or whatever, usually it is at atmospheric pressure, and also same as solid. gas is different. The pressure can change very, very easily. So usually, unless you're doing an isobaric process on a gas, which is allowed, but anything that is not isobaric on a gas, you cannot use this. So this is mainly, let me separate this even further, mainly for solid and liquid. Okay, so after you add heat, so this what tells you is you add heat, the temperature will increase. Or if you if you measure the temperature that increases, that means heat is being added to it. When heat is added to it, things can either expand or contract. So you have learned that the volume would expand according to a coefficient of expansion. What else? It depends on the initial volume and the temperature change. Okay. So this just says that this is proportional to the initial volume and proportional to the amount of temperature change. That's the constant of proportionality. I think the textbook used beta, so I'll just mimic that. Or if the object is mainly lengthwise and so it's a very long elongated object, you can directly use the linear version of this. And then you can also, if things are also changing phase from solid to liquid, then you will use the latent heat of fusion or vaporization. So this tells you how much mass you change. So if you add in a certain amount of heat, how much mass will get changed into the different phase. Okay. Let's see. All right, and then about gases. So about ideal gases, know the definition of that. That's in the notes as well. Learned it. And then there's two main equations that it follows the ideal gas law. There's two versions of it. And from the kinetic theory, you find this, which is obviously also equals to 3/2 nkt. Usually, I'll put that slightly in gray maybe, because usually this is more useful. Okay? And this can be used in conjunction with the first law that, for example, the change in E, especially usually the N and K doesn't change, so it's directly related to temperature. Okay? So now it comes time to learn the fourth thermodynamic process. So know that there are four: isothermal, isobaric, etc. Isothermal, isobaric, isovolumetric, and adiabatic. Know the definition of each. This one means temperature is 0, doesn't change. This one means pressure doesn't change. This one means volume doesn't change. This one means there's no heat in and no heat out. Okay. Now, there's some immediate consequence. For example, if delta T is 0, immediately you know that delta E is also 0. And immediately from the first law, you know that this is these two are negatively related like that. So immediately these consequences come up. If delta V is 0, if you look at the PV diagram, then there is no area under the curve. So that means immediately delta W is 0, and you can immediately conclude any energy change must be due to heat transfer. And this one, if delta Q is 0, that means, first of all, from first law, any any internal energy change must be due to work done. Another conclusion you will immediately know is because this is another definition, I should write. The change in entropy is given by this. So if it is an adiabatic process, what is the change in entropy? 0. Okay. Right, so these are the few of the key things. And what else? Right, so these are the thermodynamic processes, and maybe a thermodynamic cycle. Learn the Carnot engine, the Carnot cycle. This is important. Sort of the ultimate punchline of this topic is to look at the efficiency. So know all the four types. Just to save time, I won't go through every single one and understand what's going on. So you can also learn how to draw heat engine diagrams, which looks like this. So heat engine is taking any temperature. You need a hot and cold reservoir, and there's a certain amount of heat flowing from here to here and from here to here. Let's call the first part delta QH, delta QC, and due to that flow, you can create some work out of this, right? And the definition of efficiency is amount of useful work out of total input. So it depends whether you're looking at a refrigerator or a heat engine, what is considered useful, or even a heat pump. All these three cases, what's considered useful is different, right? So for heat engine, so I don't want to give you everything also due to time, so you can look up each of these. Refrigerator. So each of these, what's considered useful and what's considered the input may be slightly different, okay? But you can derive all these formulas. A Carnot cycle, if you put these four together, there's a key property for the Carnot cycle is QH over QC is TH over TC. Okay? I tend to write a delta in front as well, but it's easy to remember without the delta. The delta helps you with most of the mathematics that way. If you plug that into the efficiency, so a Carnot efficiency, so the efficiency for a Carnot engine will simplify all the way to this, which also gives us an indication that it is impossible to make 100% efficient for engines. Right? So maybe in the next slide, I'll also state the second law. As you can see, if you want the efficiency to be 100%, then you'll need this factor to be 0, which either you need this to be infinitely hot, or you need this to be at 0. But it is actually impossible to achieve exact 0 absolute temperature. So you will never be able to purely create heat engines that look like this. So, the second law. So there's several ways to state it. Version number 1 is heat cannot spontaneously, without an engine, go this way. Okay, so this is not allowed. Version number 2 is say that this is not allowed. And version number 3 is saying that the entropy of the universe always increases. Okay, so the entropy of the universe increases, which means, so this is the same way. You can say it like this, the delta, this is more practical, right? But you can say the entropy always increases, so the change is always positive. That means if you add up, if you're boiling the water like this, so you need to calculate the entropy of the water and the entropy of the environment. If you add up the entropy of a system plus the entropy of the environment, it will always be larger than 0, larger or equal to 0. All right. Any questions so far? So these are the key things from heat, thermal physics. Oh, right, one more thing. The microscopic view of things. There's only one formula, or kinetic theory, it's called. But basically, in an easier word, it's just saying the microscopic side of things is how do I relate the average kinetic energy to temperature? And it's basically, you have the formula that average kinetic energy is, so average kinetic energy, just this. So I can put a bar above everything, but m is usually constant, so we just have a bar above this. So this is called, right, sorry, yeah, keep going, this is 3/2 nkt, 3/2 kt, sorry, because this is average. And you can rearrange this and take the square root of this, right? And you will get 3 kt over m. Okay, just from canceling the 2, move the m to the bottom, and then take the square root. So this is called root mean square. As you can see, it's a root mean square, right? So it's very simple. It's the square root of the average of all the v squares of the gas is given by this. So you can call this root mean square velocity. So that root mean square is it's basically an average, but it's more technical type of average. It's not just adding everything and dividing by the number, just because there's a complication with the square. But conceptually, just think of it as an average, right? And it depends on this. So the higher the temperature, as you can see, the higher the average velocity things are. The heavier each particle is, this mass is the mass of each particle, the heavier it is, the slower they'll move. So everything is very intuitive over here. The thing that's not intuitive is square root, but that's from the derivation. Okay. All right, and then that brings us to the second half of the course about electrostatics. Electrostatics. So you need to know a few concepts, right? Electric force and electric fields, electric potential and electric potential energy. Force, field, potential, and potential energy. Okay. The symbols here, Fe, field is E. These are technically vectors. Potential is V, is a scalar. Potential energy is U. And sometimes we also talk about potential difference or potential energy difference. And we look at what creates E field. So the big picture is how do non-contact forces work is you have a source, the source will create a field, and then you have a test object, the test object fields the field. So there's two-step process over here. So the first step is how do sources create the field, and the second step is how does test objects react to the field. So there's a medium in between. That is something new that we learned, right? All right, so the source is, if you have a point source, then it's KQ over R square. So that's the charge of the point source. Notice this is magnitude, so make sure, technically I should put an absolute value sign here. I'll put it in orange, let's say. But usually we're lazy and so we don't put it, but understand that there is. If it is a sphere source, outside of the sphere is actually the same. I'll use the big Q. Outside of a sphere is the same. How about inside? So in the at the very end of this part, we talked about inside as well. So inside, if you have a conductor, inside the electric field is always 0. So outside would follow that formula. Now, if you have a cavity as well, if you have a hole inside, as you saw in some homework problems or the short answer problems, if you have nothing else inside, first of all, here the E is 0, inside is also 0. It's basically taking this idea to just further cut a hole. So this part is solid. You have a cavity inside here, right? You just cut a hole here, it's not going to change anything. Of course, the difference now is if you do put an extra charge in the middle, if you do put an extra point source over here, then there's no electric field due to the sphere, but there's an electric field due to this guy here. But in the conductor, it's still going to remain 0. So what if you put the orange charge here? That's no longer 0. It's basically going to be this. But inside here, it's still going to be 0. The reason is as we kind of mentioned. Let's say I put a positive charge here, then all the negative charges in the conductor, because it's free to move, it will come over here and attract just enough to cancel out this guy. So any extra, if I look at this point, if I'm interested in this point now, this, as far as this guy is concerned, it looks like everything is neutral. It just looks like there's a neutral atom over here. If there's +5 and -5, right? So it's not gonna be able to see anything. So the E field, that's why in the E field of conductors is always 0. There's E field in insulators as well. As you see, I haven't talked about insulators. Inside a insulator, that is much more complicated and it's out of the syllabus. So lucky for you guys, you don't have to learn that. Okay, so isn't it good to be a beginner physicist? Because we only care about the simplest things. Okay. So if it's insulator, you don't need to learn. Right? If your source is a plane, then it's given by this. Know the definition of this. And if the source is a line charge, it's given by this. So the type of problem one could ask is, for example, if I put a line charge over here and a line charge over here, what is the electric field over here? I could even put 3 line charge, infinite lines. Technically, these have to be very, very long. What is the E field over here? Line 1, line 2, line 3. So for line 1, this is the distance from it. For line 2, this is the distance from it. For line 3, this is the distance from it. So you use the correct distance and the correct line density, the linear charge density of each gap. How about directions? Well, directions, so remember these just give you magnitudes. So if this is a positive linear charge, it's going to create an E field vector pointing this way, E1. And if this is a negative line charge, it's going to create an E field vector going this way. And if this is a negative as well, for example, then it's going to create an E field going this way. Then you add them up vectorially. Usually we probably won't give you 3 at a time, usually at most 2, but I'm just illustrating in case, for example, if you give something like 1 and 3 and ask you the net field, then you need to add up these 2 vectors, make sure you add them up by components, or you can be given just 1 and 2, and then it's much easier to add. You just take 1 and subtract the other like that. Okay. So these are the 4 formulas for the source. And for the force, it's now very easy. It's just Q test and the external E field that it sits in. So this is how the force on the test charge would feel. Okay, so if you have a test charge here, just find out what the field is over here, and then multiply by its own charge, and you'll get the force. So for example, here now, if I put a green charge over here of 3 coulombs, what is the force it will feel? Well, find the net field and then just multiply by 3. And then you're done. You'll find the force that this guy experienced in newtons, the magnitude and the direction. You'll know both the magnitude and direction. Okay, so this is the second step of them. If you remember, if you have 2-point sources, like this, technically now you can think of what is the electric field of the first guy. It's KQS over R squared. And what is the force this guy feels on this? Well, it's Q test times the electric field, right? KQS over R squared. And you can rewrite this and you will realize this is basically Coulomb's law. Right? F equals to Q1, Q2 over R squared. So Coulomb's law is a special case of, so this is basically taking the first observation of Coulomb and breaking it down and inserting a new agent medium over here to study the idea of fields over here. Right? So Coulomb law is essentially a special case out of combining the point source and a charge reacting to a point source. If this is a physics class, the physics students will next go on to learn. So you guys have learned that the different type of sources, right? So if different sources have different formulas, the physics students will, but now you only learn that how do a point charge react to a different type of source, right? A point charge react to a line source. But you have not learned, for example, if I have a plane over here, how does a plane react to a line, or how does another line react to another line? So everything you learn is just a test charge reacting to something that is may not be the source that is may not be a point. But it does, you haven't learned what if the test object is also not a point, right? The physics students will go in and learn that. So we stop here, right? But you sort of see the line of thought that keeps going on like that, right? So, okay, and potential is due to a point source is KQ source over R, like that. That is probably the main one to learn. And although I've given you the formulas for the potential for line and plane, we probably won't test those explicitly but you will need to know the relationship between V and E. So the relationship is this. Okay, you can compare 2 point, doesn't have to be initial and final. Let's just say 2 points. This. So that means, so learn this formula. That means if E is constant, you can pull this out. And if it's one dimension and constant, if the E is only in going in one dimension, so for example, this is the easiest type that we can test you. We won't get any further more complicated than that. Then you can pull out the E and just look at the delta X that way. So right, so you pull that out. First of all, you get rid of the dot product. If everything is one dimension, that can be pulled out, and then you can know the potential difference between these 2 points is basically the distance between them, like this. So if that's the E field, so it's E times, let's say that is 8 centimeters. You plug that in here. Remember, change that to SI base units. Plug that in here, and you can get the potential difference between these 2 points. What about these 2 points? Remember, now you need to think about equipotential surfaces, that these are actually in the same potential. So don't plug in the distance over here. Look, notice that this is delta X, not delta Y. So if you do this carefully, you'll see that, because dr is dx, dy, dz, right? So if E is only in the X direction, so if it only has an X component, once you do the dot product, only the dx remains. So any Y change in Y over here, any displacement in the Y direction will not give you potential difference, only X, only along the field like this. Yeah, and that reminds me, you learn how to draw field lines and equipotential lines as well. And delta U is Q delta V. And I think I have a more comprehensive lecture on relating all these few quantities together. Okay. So now it brings us to circuits. Am I giving too much information? I'm using a lot of time. Do you like the pace I'm going at, or should I just do it more, just write down more simply? Okay, all right, good. Okay, so there is, what was the chapter number where we are at? 13, 14, and 15, good. So 13, oops, right, so yeah, so this is basically the basics of introducing a lot of, it was kind of a drier lecture, honestly, for that lecture. It's just introducing all the different words, right? What is an electric battery? Maybe I'll just say it out loud. You can make a note to fill in the definition yourself. What is an electric battery? Is a device that sets up a constant potential difference. Right? That's all we consider in physics. Current is the rate of change of charge, right? It's dq dt. Right? If the current is constant, which most of the time we are dealing with constants, one thing that is useful to take out of this course that was useful for future courses as well is, hopefully you get better at calculus as well. Understand that if d something is constant, then you can change it to delta. The reason is what does d something means? It means the slope, right? So if the slope is constant, you have a straight line. So if I ask you what's the slope at this point and look at just a change in Q and T, you see it's exactly the same thing. Now it will be different if the slope is not constant, right? Now if I look at the change in Q and change in T, it will be slightly different from, I'll draw that better. It'll be slightly different from the actual gradient. So let's make this point. So this is the actual gradient, right? The tangent to here. But if you take a dq dt, now I've exaggerated it, you're calculating this part. So this is dq dt. The other one is delta q delta t. The top one is delta q delta t. So you see, if the slope is not constant, then there is potentially a slight difference between there. So delta q delta t is, you're looking at these 2 points, whereas dq dt, you're looking at a tangent over here. But if your slope is, if your function is constant, if dq dt is constant, then this is exactly equals to delta, I won't say identical, but delta q delta t. So this is not just, I'm spending an extra 2 seconds here because this is not just useful for this, but the rest of the other parts of this course as well, and for your future course, okay, to understand that. And there's the concept of drift velocity, so 13, 14, 15. Right. What else? Resistance, Ohm's law. I think these are pretty straightforward. Let me just skip a little faster here. Yeah, so know the definition of each of them. And you won't get any formulas tested on direct and alternating current, but maybe I should put brackets and say limited examinability over here. But as you know, you sort of need to roughly know what the idea of direct and alternating currents is, especially if anything, just to honor the poor guy, Nikola Tesla, who has a huge, very tragic story, right? Just to know the idea, because later on, you need to know these effects, transformers, and generators as well. So anything sort of the basic idea that we discussed in lecture, that's enough. The textbook have some formulas about like the IRMS or the potential difference RMS of that. You don't need to know those. Light bulbs, let me just make a quick comment here, is if you ask the brightness of a light bulb, the brightness is proportional to, it's basically how much energy, right? So it must be proportional to energy or power. Okay. So if you asked about the brightness of light bulbs, then you calculate the power. Okay. Power is energy per unit time, right? Power, if you're looking at power consumed by, so in electric circuits, there's 3 different versions you can use. I'll just make a brief mention about this. You can go from the definition of dEdt to these, to the first one. Now, this one works for both batteries and resistors. Okay, so resistors is basically a placeholder for any household appliance. Right? So battery is, you'll be measuring power produced, right? And resistors, you'll be measuring power consumed. Now, you cannot use these versions for battery, the power produced by batteries, because there's no R for battery. Right? Ignore the internal resistance for now. We'll treat the internal resistance as another resistor. So assume an ideal battery, there's no R for battery, so you cannot use these. So these are only for resistors, okay? Which kind of makes sense. There's only, there's an R over here. I think that's a small subtle point I didn't mention before, but just clarify that. Okay. Chapter 14 is now, once you know the basic ideas of that, we try to torture you with circuits that have more than one loop. So if you have more than one loop and more than one battery, this is usually the hint to use Kirchhoff rules. Okay. More than one loop, more than one battery. Actually, the second one is more important because I can have a simple circuit like this, which is completely analyzable with, erase this one, without Kirchhoff rules. Right? You can just, there's only, yeah, this is, okay, I won't go into much depth, but you can do this without Kirchhoff rule. It's only when you have a second battery. Now now it becomes complicated because if I put a second battery over here, right? So you know very well, okay, so this guy is producing some potential, these guys are consuming some potential, but now it's gonna be a bit crazy if this increases or decreases for each component, right? Does the potential here increase or decrease? So Kirchhoff loop rule take care of that. So yeah, I would say this is the more telling hint of using Kirchhoff rule. Okay. There's the Kirchhoff loop rule, which is the main one, and then the junction rule, which I don't even consider the important rule because it's just staring at the currents and label for each branch, give it a name, 1, 2, 3, and look over here, just use your common sense, this I1 must equals to I2 plus I3, like that. And capacitors, know the definition of it, and know the definition of capacitance. It's the amount of charge you store per unit potential difference across it. Know how to combine them in series and parallel. That. Same for resistor. So those are also the energy stored inside is half CV squared, like that, or Q squared over C thing. QV. This is the most fundamental version technically, but all of them is basically equivalent. Okay, all right. if you notice the textbook, actually, if you look at the textbook chapters, they introduce capacitors before these, which I don't really understand. I think as you probably notice, I don't actually follow chronologically. I don't sort of word by word follow chronologically the textbook order, because I'm trying to put it in an order that tells a better story overall. And hopefully you agree, for all of you either coming to all the live lectures or you guys watching every single lecture recording. Hopefully you see that there's a story being told that is much more linear. In particular, just to justify my my decisions over here, is look at the textbook. They will first introduce static fluid, and then buoyancy, and then dynamic fluid. If you look at the chapters, you go 3, 4, 5, 6, 7, and then 8, 9, 10, like that, after some basic definition. So yeah, I would rather, buoyancy, it's on its own thing. So I'd rather discuss that separately. And it's very closely related to 3A because it's about drawing free body diagrams. And it's also very important in physics, drawing free body diagrams. So might as well introduce that right off the bat and group the moving and non-moving together. So some of these decisions are made that way. Okay, I have a question. If we come across a question, state a definition of something, writing the equation is just fine. Yes, writing the equation, but also make sure you label what the symbols mean, because different people can use different symbols. You can look more at the grading key from the topic test to get an idea how what will earn you a point and what won't. Okay, and this brings us to the last part. In case some of you missed the announcement, this last part, due to so much material being covered, and also the homework is being due sort of just a few days before it, magnetism and electromagnetic induction. I will only examine short answer questions. So I don't guarantee that it has to be from the practice short answer question. I will say 70 to 80% chance it will be selected from there, but I reserve the right to either make minor modifications or make something similar level to those. But these will be the best. I mean, I'm not trying to trick you guys. The idea is if you can do the practice, if you learn all the practice SAQ problems, you should be able to do a similar type of problem. Okay, so don't memorize the answers because I reserve the right to not choose one of the same questions, because just in case someone is just memorizing all the answers and then regurgitating that, that's yeah. Right, so hopefully that makes sense. And also, but the homework of this is due on Saturday night. So if you have, we have a 3-day late policy, right? So that will just brings us just before the final, so that will work out. And we have 8 problems, and the 8 problems are a little bit shorter, I think, than usual. So overall, it's a little shorter homework. So these are open response type questions. So basically, in my justification, whoever higher power is listening to these lectures later on, just so that you know I'm not I'm giving you your money's worth and you're actually learning the stuff. Hopefully, if you do the homework, you have learned. I will trust that sort of you learned the stuff there, and I won't put so much pressure on the final exam. So that's sort of my thinking over there. Right. So you technically still learn the stuff, especially for those who are taking the MCAT and stuff. You might need to. There might be questions about solving problems. You know, so you have some experience, and hopefully it's easier to pick up after you've done the homework. Right, so this is very similar. The first chapter, 16, is very similar to electric fields. It's looking at source and then how does test react, right? So it's the same idea that the source creates a field and the field influences the test charge. So we mainly just talked about 2 types of source. It's a line current or infinite solenoid. So if it's a line, it's mu naught over I 2 pi r. And this is mu naught Ni, where n is the number density, a number of turns per unit length. Right? So these are the source. So you see current is the primary source of magnetic fields. All right. So this Tesla meter, you can measure these things. Technically, there's also permanent magnet. They can create external B fields, but we don't have formulas for those. So if it's a field generated by a permanent magnet, we'll just directly tell you how many Teslas that is. But if it's generated by a current, if it is a magnetic field generated by a current, like that, then there's actually a way to relate the current to the field strength, to the magnetic field strength. Right? It also inversely depends on distance, directly depending on the source current that way. Okay. Toroid, I don't know if I might or might not examine it. I'll put it here just in case. It's basically an infinite solenoid. I'll put in brackets because it's not really that new a formula. You can treat it as a new formula, but it's a clever way to make an infinite solenoid, so you get rid of all the edge effects by connecting them together. So now what is the length of this solenoid? The length is 2 pi r, where this is r. I think in the short answer question, one of them asks you the circumference. So if that's the case, then just put the circumference over here, because the circumference is the length of the solenoid. So that's why it's important to know what the variables mean and not just remember, oh, r is radius. You know, that is a bad way of thinking. R is the perpendicular distance away from the wire. What do we mean by perpendicular distance? I think some of you asked before. It's you measure perpendicular from here, because if I ask you what's the distance this point from the wire, well, you might measure perpendicularly from there. Someone else might be measuring this, right? A hypotenuse, like with Pythagoras diagonal over here, right? That's not what this R stands for. So that's why sometimes we specify this as perpendicular. If you forgot that word, we won't deduct any points, of course. But if you specify it, even better. Right? So what these symbols mean is more important than what they are. So because if the problem gives you a D, don't write R in it. You're not using the symbols that they're giving you, right? So that's not a good habit. So here the length. This is the length of the solenoid. Length of the solenoid. So you can only use this version if it is technically if it's a finite, but a finite and very long one. Then this is a good approximation. If it's really truly infinite, you don't really have length, and the number of terms would be infinite if it goes on forever, right? So you have infinity over infinity. You don't know what to do with that. But I can tell you each centimeter or each meter, there's 50 terms per meter. You know, so this is a finite number. So if it's true infinite, you can use this. So this is kind of sort of a halfway point, right? So it's like an infinite, so you can use this. And the length is, yeah, the circumference, which of course you can, if the question don't give you the circumference, they give you r, the radius of this, then you put in, you rewrite this like that. Okay? Don't get confused with this formula with this formula, even though they look very similar. Now you understand they mean completely different things, right? Okay, all right, and then, yeah, and then the test, now what, unlike the electric field chapter, where the thing that is always responding to the field, to the electric field, was a charge, was a test charge, right? And I told you, I just hinted earlier, like 10 minutes ago, that physicists would go on to learn, oh, how about a wire? How does that react to a field? How about a plane? How does that react to a field? You don't learn that. But in magnetic chapter, you learn actually two things. How does a test current react to the field, and how does a test charge react to a field? That's why you have two formulas here, right? As opposed to just this for electric field. So you have one for test charge. Okay. If this side is a vector, this side has to be a vector. So this, I have the option to not put the vector on because this is proportional. But here, if you don't put the vector sign on, the magnitude is this. Okay. I won't go into much of the explanation, but you can review the lectures of where that comes from. Okay. So this is how a test charge reacts. This is how a test wire or a test current react to the external B fields. Okay. So this is the length of the wire that is in the presence of that external B field. This is the velocity of the test charge that is in the presence of that external B field. Okay, all right, and learn either the left-hand rule or the right-hand rule. I'll sort of stick with these two, although some of you who have done more research will realize there's actually many mnemonic devices to solve this. People come up with lots of creative ideas. It's up to you. If those work for you, that's fine. My recommendation is just stick with what we were taught, so to keep things simple. Here, if there's also there's one more right-hand rule. So there's 3 hand rules in total, in some sense. I guess 4 actually, let's say. So there's one for each here as well. The first one, you put your thumb on it. It will tell you how around the source current, and they'll tell you how the field that is generated from the source goes, right? And the infinite solenoid is basically, if you have an infinite solenoid, it creates an effective permanent magnet. So if you have this, it'll create a B field that goes like this. So you have sort of like a north and a south pole. So this is like that's called the effective north pole and effective south pole on both sides. So you, yeah. So what you do this time is you flip your hand, you turn your hand roll around, and actually your thumb is going to tell you the direction of the B field, and your fingers, excuse my diagrams. I think I have enough practice in drawing decent hands. But you're going to wrap your hands around the source current this time, and it will tell you the B field generated from it. It is a little bit confusing, but actually after a while, you'll see they're kind of intuitive. If I give you a solenoid and ask you to wrap your right hand around it, there's only one way that is logical to do that, right? You wouldn't try to wrap your fingers around the blue B fields over here, right? There's only one logical way to wrap your hand around this. So it's ultimately it's sort of very intuitive. And if I give you a wire, there's only one logical way to sort of use your hand rule. It's to wrap it around here. So it will automatically tell you which one is which. So Yeah, so technically there's 4 different rules over here, but hopefully, yeah, that makes sense. And then last bit is electromagnetic induction. Learn the 3 formulas that you need, the definition of flux. An easy short answer question that can easily ask you is, if I have a current loop like this, and there's fields going just parallelly across it, and then you rotate it to like this, and then now there's fields going through it, does the flux increase or decrease? You know, it can be a simple question like that. And then it will induce an EMF. This is not definition, sorry. It will induce an EMF if there's any change in flux. The minus sign reminds us that the direction of current that gets induced will always opposes the change in flux. So whatever this is, the minus sign is not to be taken too seriously other than that. So to get the induced current, it depends on whatever resistance you have in your circuit. Resistance of the circuit. It can be the wire or some actually components. And we put this to use with the transformer equation. And no, this is not about robot cars, but the ability to step up and step down transformers. All right, so that's pretty much all I have for the review. Sorry, this went on longer as usual, but I think I forgot to show you some pictures of actual transformers from last time. So you can see these, you'll probably be more familiar with these, sometimes seeing these on the streets. These are basically transformers stepping up the current to these transmission lines, these power lines, and they get transferred over cross country, and then they step it down again. Okay. All right, any questions? All right, if not, let's see. I know I'm short on time, but I still want to cover, just give you a overview of Gauss's law and Ampere's law, because it is in some sense my responsibility to cover in the class. So let me do that as well, and then I will see if I can do 2 or 3 problems. Even if this overruns a little bit, I'll keep that in the recording, okay? All right, so really we are trying to address where these magic formulas come from. So this part, if you like, you can either just listen to this, or if you'd like to take some notes in case you need this for take the MCAT in the future, then that will also be okay. So we know that for point sources, this is the formula for it. For planes, this is the formula for it. And for lines, this is the formula for it. Ampere's law explains where these 2 formulas come from for a line and for a solenoid. So basically I'll write this version first. So basically these magic formulas are basically coming from 2 fundamental laws, one for electric and one for magnetic. Okay? And the law looks like this. So what I'll do is I'll just demonstrate this for you. If you need to learn this in the future, you can refer to this part of the video. If you don't need to, you can just treat the next 10 minutes, maybe 5 minutes each, as just understanding. Okay. So this is Gauss's law, but a lot of textbooks forget to write one thing, which I think is extremely useful, is to put an S next to it, right? And what that means is we're looking at an imaginary surface to do the integral in. So this is an integral, as you know, but it looks very scary. So let me disentangle this for you. So first of all, anytime you write down an integral in physics, you need to write boundaries, whether it's from one point to another, from initial state to final state, or whatever. You need to write down the boundary, what you are integrating with respect to. Where's your starting point, where's your ending point? Okay. Now this is something called a surface integral. So A stands for area. So this is, if you have dA over here, this is called a surface integral. So a surface integral means you don't, normally when you have X and Y and you want to find the area under the curve, then you have 2 points, right? But if you have a surface integral, your boundaries are not 2 points. It's not like a line like this from initial to final. It's a whole surface. So this is called Gaussian surface, just to credit Gauss, who came up with the mathematics of this. But it's not a real surface, it's an imaginary surface that where we basically telling us where is our starting point and where is our ending point. Just like A and B, there might be physical significance, but it's just basically telling you where to start, where to end your integral. A lot of textbooks treat this as understood and they don't write it there. But however, I think it's very important and it makes your life much easier. Again, a lot of these extra works I tips that I give you are not to make your life more complicated, it's to make your life easier. It's just to make the things clearer in the front end, so then the back end, it becomes easier, okay? So what this stands for is the charge enclosed, is the amount of charge enclosed in where? Enclosed inside that surface. So this is a mirror over here. Whatever's about the surface on this side, this has to be about the same surface, okay? Inside or enclosed in S. Okay. Epsilon naught is a fundamental constant that you know, it's permittivity of free space, and E is the electric field. All right. So what does this scary thing do? Let's look at a source. So this is the goal. I want to find out where this comes from. All right. So I'll look at a source charge. So let's say this guy has charge Q. So let me draw its electric field lines first. So its electric field line looks like this. And now I'm interested in finding the electric field at some point here, let's say distance r away. This is my goal. Okay, so what we do is we just plug and chug into Gauss's law. And what you'll realize is this one law will give us everything, not only the three that we introduced, but give us every possible electric field we need to know in the future. Of course, you just need to know these three to learn these three, but this is one law that rules them all, basically. It gives you everything, okay? So we'll see how that works. So first of all, I need to define a surface that goes through here. Notice there's a dot product here. So a dot product means that if your surface area is, the area vector is parallel to E, this thing will simplify a lot, right? Because you know dot product becomes E dA cosine theta. By the way, this is called electric flux. Remember, magnetic flux is B dot A. This is E dot A, so it's an electric flux. Okay? So that's why sometimes we put a subscript B if you're talking about electric flux. Of course, this is a small area, but it's the same idea. Okay? So what you want is really, you want the area, the electric field to go in the same direction as the area vector, because that will mean this side would just become EDA, and it's much nicer. So can I find a surface where the area is always, the area vector is always parallel to the electric field vector? Yes, I can. All I need to do is wrap around a sphere like this, around it. And as you can see on this sphere, at every point over here, the area vector, right? If I look at a little piece of area at every single point, the little piece of area is going to be parallel to the electric field vector at that point. Okay, does that make sense? This helps your understanding with magnetic flux as well, so it's not a complete waste of time. All right, so I will choose this to be my integrating surface, my Gaussian surface to integrate around, so I'll call this S, and then I will plug it into the equation. So at first, we'll look at this. I'll use more space over here. So first, let S be a sphere of radius r. Why radius r? Is because I want to find the electric field at this point. So if I want to find the electric field at this point, then I better draw a Gaussian surface that goes through this point, because otherwise I'll be finding the electric field at a different point. So that's why I'm choosing the Gaussian surface to go all the way to be a sphere, S to be a sphere of radius r, like that. Okay. All right, so let's just solve the left-hand side and the right-hand side separately. Let's look at what the left-hand side equals to and then match it up with the right-hand side. So the left-hand side, actually let's do the right-hand side first, it's easier. So the right-hand side says I need the total charge enclosed inside my surface. What's the charge inside my surface here? The charge inside is just Q, right? Little q. So all I have to do is, so the right-hand side is equals to Q over epsilon naught. It's a constant. And that's the end of the story. That's it. So now let's do the complicated side. All right. So first of all, this becomes this. Since E is parallel to dA, right? I've chosen wisely. I've chosen on S. E is not always parallel to dA, but if I've chosen the S wisely, then this is always parallel to this. So the dot product becomes just a normal product. Now, I'm going to claim I can pull the E out of the integral. Why? When can you pull something out? Is when E is constant. But is E constant? E shouldn't be constant, right? Because the further away you go, E should be stronger or weaker? Weaker, right? So the further away, the electric field should be weaker and weaker. So it's not constant, but the key thing is this. With respect to my integral, S, it is constant. So it's constant on S. Why? Because I've chosen wisely again. I've chosen this sphere that is so symmetrical that there's no reason that E is stronger on top than the bottom. It's the same radius. So on S, that's why this is so important of labeling the S over here. You're allowed to pull it out. Otherwise, I don't understand how you would justify yourself pulling the E out if you don't have S labeled over here, right? But if you do, now you can pull it out because E is constant on S. Now, how do you integrate this? Well, don't be afraid. What is the integral of this? Can someone tell me what is integral dx? It's just x, right? What is the integral of dy? It's just y. What's the integral of dA? It's just a. So that's it, all right? It looks scary the first time, but now you see this simplifies down to here. Now, technically, I need to put in the boundaries as well, right? So I need to put in the initial and final state. So this time I'll write down the boundary S like this, okay? So what is the area of S? Well, the area of S is a sphere. Remember I said S is a sphere of radius r. So now you just plug in 4 pi r squared, right? Because this is the area of S. All right, that's as far as I can go. Now let's just remember I need this side should equal to this side. The left-hand side should equal to the right-hand side. So let's put them back together. So E 4 pi r. Notice this E is the vector sign is no more. It's a magnitude over here. So just to point that out. And what is my goal? My goal is to solve for E, right? That's what's my goal. And I have this formula. Remember 1 over 4 pi epsilon is basically K. So that's where this comes about, okay? And then, so that's where that comes from. I'll just roughly go through the rest in a very quick manner. If you have a wire like this, you can draw the electric fields, which is now perpendicularly pointing away. Assume it's positive, let's say. So assume this is positive wire. And now let me choose a Gaussian surface in a slightly more interesting way, like this. So this time my Gaussian surface is a bit complicated. I have the top surface, I have a bottom surface, and I have a middle surface. So let S equals to S top plus S bottom plus S middle be a cylinder around the wire. Okay. So I can rewrite Gauss's law like this and ask myself, let's start with the right-hand side again, that's easier. What is the charge enclosed inside inside S? So everything add together. So these three together, it's called S. So what's the charge inside here? So I want to express myself in terms of line density, right? So let's say this has a line charge density lambda, which is amount of charge per unit length, right? So the charge inside here depends on the length. So the charge in S is lambda times the L of the length of S. Okay. So this side, the right-hand side is just lambda L, the length of S, over epsilon naught. And let's do the left-hand side. So this time I have an extra step before I can break the vector sign. This little circle means I need to add everything together. So I have actually 3 integrals. You will first break this up into 3 pieces. S middle, EDA, okay? And analyze each pieces one at a time because this S is comprised of these 3 pieces. Okay, so what's on the top? The top piece, the area vector on here is pointing this way. But the fields are pointing, so at any point over here, the electric field is pointing this way, which means the dot product gives you 0. So this actually gives you 0 because E is perpendicular to dA on S top. And same as the bottom, the area is pointing this way, whereas the fields are pointing this way. So this again goes to 0 because E is perpendicular to dA on S bottom. How about on the middle or on the side? The area, pick a point anywhere here, the area is pointing perpendicularly away. Now the field is actually parallel to it. So you have 0 plus 0 plus the last one is just EDA, like this. And then we can go through the same logic. Can we pull E out? Yes, it's a constant because look at the symmetry of the problem. There's no reason why E here is stronger than E here or on the other side. Everything is very symmetrical. So you can pull E out and integrate dA, which is A of the area of the middle part. The middle part here is a cylinder that wraps around it, right? So this is the imaginary cylinder that's wrapping around it. What's the area of a cylinder? Well, it's 2 pi r, r being the circumference. So this is, let's say this is r. So I'm finding the electric field somewhere a distance r away. So this is 2 pi r times L, the length of the Gaussian surface. Now let's match it up with the left-hand side. So you have E 2 pi r L over lambda L over epsilon naught. The L's cancel, make E the subject, and you get our formula. Okay, so maybe I won't go for the plain one, but hopefully I've convinced you that you see all these formulas actually came from one law. So Gauss's law, it's actually something very deep. It's a fundamental law, and it's one of the 4 Maxwell's equation. And so there's Gauss's law, Ampere's law, and Faraday-Lenz law. And there's one that's called the no magnetic monopole law. So technically in this class, we have actually talked about all 4 of them roughly, at least briefly. These 4 Maxwell's equations is basically everything you need, not you, but everything physicists need to know about anything to do with E and M, electromagnetism. Everything in the world that we know about electromagnetism is derived from these 4 fundamental laws. And as far as we know, these are quite, at least in classical physics, these are fundamental laws. And yeah, they can actually be combined with we write it into one bigger law, but this is sort of good enough at this moment. All right. Ampere law is the same idea, but maybe I won't go through the details. But it's sort of the same idea to build it up. So if anyone needs to take an MCAT exam on these, hopefully this gives you a little bit of momentum to know where to start. You can refer to these steps in the previous slides that I've covered. If you don't need to take the MCAT exam, well, congratulations. And I'll stop over here in terms of the content. All right. Okay, so let's see. I'll do what I promised and do at least maybe. I will do at least. I'll do at least 2. We'll see how much we can do. All right. Let me change it to a white background as well. So it will mimic a little bit more how you do your problems. So first, with test 4, question 22, I think you mean practice tests, so that's fine. So, question 22. Whoever voted on these problems, let me know if I'm solving the right one, just in case you actually mean something else. Okay, so 22 is this. Okay, good. A lot of you actually asked about this one, so that's good. Right, so there is, first, let's redraw it out over here. And is there, do you want me to do all parts, or maybe, actually, can someone suggest which variation? I'll do all parts, but which variation do you particularly want to see? Maybe one is more difficult than the other. I don't know. I want to see. Practice 4. C. Yeah, definitely. But which variation in terms of the charges? 3 and 5 plus 3 minus 5 minus 3 plus 5. 3 minus 5. Okay. So 3, and then here we have a Q net. Is minus 5. Okay, so we do need to go through A and B first. So if here is plus 3, then it will attract minus 3 over here because it's a conductor. So it can always do that because conductors have infinite many, an idealized conductor have infinitely many positive charges, infinitely many negative charges. So it can always attract that much to here. So on R1, so the Q on R1 is minus 3 coulombs or microcoulombs. And now, if you have minus 3 here, how much, the whole thing has to be minus 5. So if minus 3 has migrated over here, so you're left with minus 2 on the other side. Okay, so the Q on R2 is -2. Let's see. As a quick check, what you want to do with these type of problems is do this. Is quickly add up the Q on R1 plus the Q on R2. So add up the charges. The charges on conductors, as you learned from one of the properties, it has to be on the surface. It's not going to be net charge are not going to be floating in the middle. So add these two up, they should equals back to the total net charges there, like that. Okay. So you can do a quick verification, -3 plus -2 -5. Good. Okay. And then now the electric field. All right. So first of all, the middle part is the easiest. This is a conductor, it will always be 0. With Gauss's law, this is also useful. We now understand that if I look at a Gaussian surface over here, it's actually, this is the correct explanation that I was not able to do without Gauss's law, is if I want to find the electric field over here, notice Gauss's law tells you that, let's call this a Gaussian surface S, the E field, I technically need to go through the algebra, but I won't. So I'll just show you that the charge enclosed inside S, what is the total charge enclosed inside S? Well, the total charge enclosed inside S is you have a +3 and -3, right? That's the total charge. So this is 0. So if the right-hand side is 0, technically you need to go through the few algebra to simplify the integral, but you can already see the area is not 0. The area of S is not 0. So the E on S must be 0. So this is the real reason why the electric fields are 0. And this works for all conductors. No matter what charge configuration you put, this they will move around in a way that this is always true, right? So for part C, part 2, E in the middle is 0. Electric field strength. So I don't need to talk about direction. If there's no electric field strength, no electric field vectors, there's no magnitude, no direction, right? There's nothing. There's no electric field. End of story. Right. How about in the middle? Well, we said the hollow part of the conductor is not going to contribute any electric fields. So the only electric field contribution is from the +3. Okay. So you can basically the line of thought, the logic of thought is the total field in the middle is due to the point source plus due to the sphere shell, right? But this guy is going to be 0 inside the hollow part. So you only have KQ over R squared. And this Q is +3 coulombs. Any questions about this? State the electric field magnitude and direction at a distance R from the center, right? So what I would state is, I will state this as K3 mu over R. Since they didn't give me what radius that they are interested in, so we're looking at the point over here and asking what's the electric field. They didn't say, they just say R, that is smaller than R1. All right, so we'll label everything R1, R2. And we just need to find the R, right? So we'll keep that as R. If you like, you can write K is 9 times 10 to the power of 9. If you like, you can write mu is 10 to the power of 6, -6, sorry. Yeah. So you can plug those in, but it doesn't matter. Either way, because we're not using a computer to grade in the final, we're using humans to actually look at your answer. So anything that makes sense, this is the better thing about human grading, and we'll be able to give you the answers, the grades. And direction, yeah. So if this is positive charge, so only this guy contributes, there's no electric field for this guy. So if this is positive, over here, the field would be pointing outwards. So the word is radially outwards. And finally, outside over here, you can pick a point here. All right, what is the field? So this time, again, you go through the same train of thought. The points, so technically everything should be vector due to the sphere. Okay. Let's look at direction first. So first of all, should both be considered? The answer is yes, because outside we have a formula for the sphere. The point charge, we have a formula for that, so both have to be considered. Now let's draw a free body diagram here. Which way is it pointing? Here, originally, there's only one contribution, right? But for this point, there is a contribution from the point charge, and there's a contribution from this outside the sphere. Outside of sphere. And they are opposite because the sphere has a net negative charge, so it will produce a vector that is pointing inwards like that. Okay. So now you just have to add these up. So the magnitude is going to be, let's say the magnitude is outwards. Let's do out minus in. So it's E point minus E shell, right? So E point charge is Q over R squared. R being this time we're using a different R. Let's call that R prime. Minus K, and then the Q of the shell, okay, minus over R prime squared. So this can be simplified a little bit like this. Right? And let's plug in the numbers that we have. So this is 3 mu minus the magnitude of, notice this is magnitude, right? So technically there is a absolute value situation going on over here. So this is actually there. Okay, so technically you plug in -5, but the absolute value turns that into +5. Okay. So it's 3 minus 5, so you have -2. But overall, it has to be positive. So there's a little bit of fudging over here, but if you know what, so this requires you to actually know what you're doing. This is a magnitude, so the result is K2 mu over R prime squared, like that. Any questions on this? Okay. Otherwise, I've done 1 out of 2. Any follow-up questions? Test 321. Okay, we're good. Okay, so test 3, question 21. Again, whoever voted for this, see if you can tell me which variation you want. Do you want the potential difference between AB, BC, or AC? AC, okay, good. Let's just copying out what we're given. So we're given E is -5I. So you see, this is newtons per coulomb, so it's a SI unit. So the first thing is I don't write that because it's a SI base unit. The next thing is I'd like to write vectors in a column if possible. So I'll write it as -500 like this. Okay. So I'm dropping the newton per coulomb and I write this as a column like this, and it's more intuitive for me. And then it's asking for the electric potential difference between A and C, right? Okay, good. So the potential difference, we start from the formula. So this time we want A and C. So let's put A and C, like this. Okay, so where's C? Right, C is here, is -3 and 4, and A is somewhere here, 4 and 1. Okay. So the rest is basically the mathematics of this. So I'll just plug this in. So 4 and 1, -3 and 4. I could actually keep it as A and C first. It's up to you. Yeah, I'll show you different ways. So here you have -500. dr is just a little displacement in x, y, and z. Okay. So what is r, in case you're confused with this? R is the vector from the origin to any point. Okay. So technically, if you think about it, it's x, let's do 2D first. It's x and y, right? So r is the vector. It's called a position vector. So it's x units to the right and y units to the top. dr is a small bit of this. So take a small segment of that. So a small segment of that is just a small segment to the right and a small segment to the top, something like that. Okay. So that's where that comes from. Okay. All right, now do the dot product. Maybe I should have just kept this as A and C, so I don't have to write so many things. So this times dx plus 0 times dy, which is 0, and 0 times dz, which is 0. Okay. The 5 is easy enough. We can pull that out. Okay. 4, 1. I regretted copying this out now, but I should have just put an A and C so I can write less things until the last step. Until I need it. But anyway, so now you integrate x dx. Right? It's just x 4, 1 and -3, 4. All right. So what do we plug in over here? So keep in mind this is C, this is A, right? So do we plug in? What do you think in the chat? Do I plug in -3 or do I plug in the 4 into the x value over here? Which one is x? There, that's right. So -3. So we plug in -3 and minus, and then 4. Okay. So this is -7 So 7 times 5 is 37. So negative, negative, positive. So that's positive 35. What is this the end of the story? Is this done? Or do I need to add something else? What am I missing? Is this the final answer? If you solve something, you will always need to put in units, right? What is the right unit for this? Potential difference? Volts, exactly. There we go, yeah. A different way you can write it, if you just keep this, if you were more clever than me, just so keep it as A and C, so you write less things. What you can do is go down to this step and then just plug in this. So think of it as the x value of C and the x value of A, right? And then plug it in over here. The x value of C is -3, and the x value of A is 4. Yeah, so you get the same answer. So that's a little bit less writing, but hopefully the math is the same. You can write it in a million different ways. I can make a quick comment on B as well. Right? So this is 4, 4. Yeah, 4, 4. Notice if I change this into B, if I change A into B, so let's do B over here. The x value for B is also 4, right? So I will get the exact same answer out of this. I'll get 35 volts out of this, the potential difference. So what is that telling me? The potential difference between A and C is the same as the potential difference between A and B. And that makes complete sense because where's the equipotential surfaces? Like this. It's perpendicular to the electric field lines, right? So the electric field lines are going this way. It's -5 to the x direction. So these are the equipotential lines. So the potential difference between C and B must be the same. So this is an extra verification that the potential difference between BC is the same as AC. You can try to repeat this and calculate difference between AB. Do these 1, 2, 3, 4, 5, 6, 7. Do these 7 steps, and you should get 0 because there should be no potential difference between here. Okay. All right. How do we feel? Should we do one more? Let's do one more. Let's see. At least I take care of all the 3, at least 3 votes at once. So test 2, SAQ, question 32. Sketch a PV diagram of isothermal something and adiabatic something. All right. Can I do everything, or is there a particular variation? Let me know if there's a particular variation you want me to do on the same graph. Clearly label which curve is which, as well as which direction. All right. Practice 2, question 32. Oh, okay. There's a question from the previous question. So V is minus EDL. Yes. Right. I forgot to think about that. The sign of V. All right. I'll give you a hint. Is what I usually do is I calculate the magnitude first, and then I think about should it be positive or negative. Okay. But I forgot to do that. So bad habit for me. All right. So you agree that if I have a minus sign in front, that basically, it's the difference between, am I finding the potential difference between B and C or C and B? So one is the negative of the other. All right. So the magnitude is going to be this number. The absolute value is definitely going to be this number. All right. So let's determine, should it be positive or negative? This is how I figure it out. I will imagine I have a positive test charge like this. All right. So I'll put it over here and ask myself, which way will it go? All right. This guy will go this way, right? It will go from right to left. So because of the electric field. So I can tell from the electric field that this guy will move from this way to this way. Agree? Now, how about, so in terms of fields, it's telling me the positive charge would move this way. How about in terms of potential? Can I infer which way is the potential higher? Is the potential higher at A and at B, or is the potential higher at C? What do you guys think? Remember, this is a positive charge. If it goes to the left, if the electric field is telling me it automatically goes to the left, which one is higher? Which side is higher potential? In terms of the potential perspective, that's right. The A or B is high potential. This is low potential. All right, so it's asking me for the, all right, so it depends if it is asking for VC minus VA or VA minus VC. So if it is asking for VC minus VA, I better get a negative number. So that would be negative 35 volts. If it asks for VA minus VC, that will be positive 35 volts. Now, that question before, I think it did not actually specify that which, yeah, it just says, so it's a little bit ambiguous, right? It just says the difference between the points. All right, so that means so the answer is both is okay. We'll accept both answers because it's basically this question is not trying to test your knowledge about how to determine which way is higher or lower. It's just this question being a short answer question, it's more concerned with you able to just do these 7 steps. If you are quicker, by the way, you can actually skip 1 or 2 steps. It might just be 5 after you've done some practice. But since this is a explanation, I want to go through each detailed step very, very quickly. Otherwise, from this step, you can maybe skip a step or something like that to get the answer. Yeah. So the point of this question, kind of just from reading this, I'm guessing it is more concerned about asking you to do that mathematics than to determine the sign. Yeah. So it's almost like asking you what is the distance between your home and UCI and campus. So so technically you say should I look at the x coordinate of the campus minus my home or my home minus the campus? So sometimes we don't really care which one minus which one. We just want the difference. Well, what's the distance between it, right? So that's a little bit like an analogy over here. We're more caring about can you calculate a potential difference. If this is an open response question and then ask you maybe there's an even follow up and ask you how fast would this move after, or how much kinetic energy will it lose? If it starts let's do a quick variant on this in case this is a bigger question, like open response question. And I say, let's start with the velocity v naught is 0 meters per second. What is the v final? Let's call it v initial and v final, right? So what you do is, I now know the potential difference. I need to find the potential energy difference. So the potential energy difference is Q times delta V. So it depends on my charge. Let's say it's an electron, right? So electron is 1.6 times 10 to the minus 19 coulomb, right? So 10, yeah, so that's negative 1.6 times 10 to the minus 16 for electron, and then 35, all right? So I get a number over here, you plug in a calculator, all right? So now I'm going to ask myself, should I put a positive or negative sign here? All right, let's make this a proton, because otherwise I need to flip my arrow to the other way. It's going to go the other way, right? So this is the charge of a proton and positive. Okay, so should I be positive or negative over here? All right, so let me see. Is it gaining or losing potential energy from here to here? Is it gaining or losing kinetic energy? Well, it should be gaining kinetic energy, right? It automatically moves from high to low. So here it's going to be fast, here it's going to be slow or at rest, right? So it gains kinetic energy. So I will think about the physics separately from my math, right? It'll gain kinetic energy, and that means it will lose. It must, because of conservation energy, it must be losing the electric potential energy. So it's transferring the potential energy into kinetic energy, right? So it kind of makes sense. It's going from high to low, right? So at the end, I will say the delta U of the particle, of the proton, or the particle that you're interested in, it doesn't have to be, it's going to be, what did I say? It's losing potential energy. So losing meaning final minus initial. Final is smaller, right? Initial is higher, so this should be negative of whatever number I get over here. Okay, so here, notice I didn't put any subscript. I'm just doing the math first. Now I'm gonna do the physics part and interpret that. Okay, does that make sense? So I figured out that it's losing potential energy, and then I'll put a negative sign in here. And that means from conservation of energy, it's gonna be gaining. So there'll be a positive sign and put in the same number, like that, of the proton. The proton's kinetic energy change would be positive. It goes from slow to fast. Does that answer your question? Does that help? I guess I've gone beyond your question. Okay. What was 20? What was 32 again? 32 is, okay, the PV diagram of this. I can do both, isothermal and adiabatic. So isotherms look like this. They're like 1 over V graphs. Okay. So these are isotherms. So just pick, I always start with the isotherm. That's easy to draw. So just draw any one like this. And then adiabatic is steeper. So so 2 things you need to know. Learn that isotherms are basically like P is 1 over V, right? So P is NKT over V. So if you have a constant temperature, then it follows sort of 1 over V graphs. The second thing is learn that adiabatic is steeper than isotherms. Okay. So if this is an expansion, let's start from somewhere with a small volume to move to a large volume, right? So it should expand, but it should be steeper. So it will go like this. What else? It needs, so just to go through the details, it says on your diagram label PAVA. All right, so let's call it, use what their suggested variables. PA, VA, and then PB, VB. Let's just satisfy all the conditions, right? So VB for your initial state and PB, VB for your final state. Oh, sorry, I was looking at I was looking at 33 and 32 at the same time. Yeah, I was answering half of each. Sorry. Yeah, so this is a isothermal expansion. This is an adiabatic expansion. Right. Is there a particular variation of something expansion or something compression that you want to see instead of me doing 4 times 2, 8 variations? There's no suggestion. I think I can actually just do it quickly. So so if this is, maybe let's yeah. If this is starting point, so isothermal expansion is this, adiabatic expansion is this, isobaric expansion is this. Isobaric. All of these are expansion. As you can see, expansion just means you start from a smaller volume to a larger volume. Isovolumetric clearly doesn't have expansion or contraction or compression. So you can either just sort of think of isovolumetric decrease in pressure or isovolumetric increase in pressure. So that's the only 2 ways we can talk about. Or some textbooks call it isovolumetric pressurization or isovolumetric depressurization. How about compression? Just keep in mind, compression doesn't make sense for isovolumetric. So let's start from a high volume because we want to compress it. Right? So isothermal, it's just reverse the isotherm. Adiabatic is steeper. So if I want to start with the same volume and end at the same volume, let's say they all end at the same, start at the same volume and end at the same volume. So adiabatic has to be steeper. And isobaric is the least steep. It's the one that's flat because it has to go the same pressure. So these are called isobars, isotherms, and adiabats. Okay. All right, any questions? All right, good. Is there anything else you're dying to ask? Here's your last chance that I can see communicating with you guys. All right, I think either we're very happy or we're very tired. So I'll let you go either way. And thank you very much for the whole quarter. It's a real good pleasure to teach you guys. Hope you guys took a lot out of this, whether it's hard skills or soft skills from this course. Okay, all right, thank you very much. I'll stop the recording now. And if you have a few questions, I'll stay for just another minute. You can turn on your volume and ask me. It'll probably be more efficient. All right, otherwise, have a good day, have a good quarter, and see you guys. Good luck. Bye.